in this case, we don't have focal lengths, right? So what we talked about earlier was that all of the light is coming in straight to this lens is going to split up. It's going to diverge. It is not going to focus at a single point. So instead of having focal lengths, what we have are points of curvature. And all that means is if this is part of a circle right here on one side, the center of that circle could be right here. And the same thing on this end, right there. So instead of having focal lengths, we have points of curvature. Does that make sense? So what happens now is that we have the same, well, we'll put an object right here. It can be inside of the point of curvature or outside. For divergent lenses, it does not matter. But basically, this is going to work the same way. We're going to have a parallel line going in that will shoot off away from the central axis, and then we will have we will have one that goes like this, and then shoots off further, and one that goes through the center. And in the same way that we had earlier, sort of backtracked from these lines, we're going to backtrack again, and this is going to come out looking something like this. So what we see here is that the object is again creating a virtual image, an image that is right side up on the same side of the lens as the object, but this time it is smaller. And this is one of the bigger differences between convergent and divergent lenses, is that the divergent lens will make an image that is smaller than the real object, and a convergent lens, the type that we just did before this, made, if you remember, the image was bigger and removed from the object. So these are basically some of the basic ways that lenses take an object and create an image, either real or virtual, from it. So these ray diagrams are a very important tool to understanding how lenses work. I'm going to introduce two equations real quickly. And these equations work with the ray diagrams that we just did. The first is just the thin lens equation, right? So we were talking about objects being within or outside of a focal length, or a point of curvature, and then an image being made at some point, right? The equation relating these distances, which we didn't go into, is the thin lens equation. So basically, 1 over the focal length equals 1 over the distance the object is from the lens plus 1 over the distance the image is from the lens. So this is a very straightforward approach to finding how far an image is from a lens given the original object. And then the second equation that I'll give you, actually, you don't need this up here for any longer. Straightforward. Okay, so P is, so this is a focal length, okay? P is the distance that the object is from the lens, and I is the distance that the image is from the lens, okay? Alright. And then the second equation I'll give you is what's called the lens maker's equation, which returns to the index of refraction and some of the material that you were working with earlier. So it's the same 1 over the focal length equals the index of refraction minus 1 times 1 over R1 plus R2. Now, R1 and R2 are the, respective radiuses of curves of either side of the lens. So basically what that means is for the convergent lens that we talked about, R1 would be the radius of curvature the side closest to the object. And R2 would be the radius of curvature for the side furthest from the object. So if you remember this, if you have an object, this is the side closest to the object. So this radius is the R1 that we're talking about. R2 is this radius for this side that's a little bit further away. So given, yeah?
Are these curves from circles or from parabolas?
They are from circles.
Okay.
Well, for ideal lenses, they're from circles, right? So everything that I've talked about so far is given a circular curvature of the lens, yeah.
Okay.
Real lenses vary from this quite a bit, but as far as the, I guess, most basic aspect of lenses, we're going to talk about circular curves. So, so given these two radiuses and the index of refraction, basically of the material that we're talking about, if it's a glass lens or if it's a diamond lens, you know that index of refraction. Given that, you can find the focal length. And given that focal length, you can use the first equation I gave you, the film lens equation, to